Okay, so Chapter 8 on calculating deflections. So the first thing you need to do is you need to be able to draw a deflected shape without getting into calculations. So some of the problems are very straightforward. You can do that. And some problems become a little bit complicated. You have to guess. But getting the deflected shape is quite important in helping you to further calculate the displacement and rotation angle if you want to. So we talk about how you can draw the deflected shape without getting into calculations based on some sort of knowledge that you should have. So we also talk about the assumptions that we adopt for frame structures. And we get into the detailed calculations now. So basically, there are 4 methods that we can use. So direct integrations, you know pretty well. It's pretty much a straightforward applications of moment curvature relationship, imposing boundary conditions, and you can get the displacement rotation angle. So we say that that method, although it's very straightforward, but it has its limitations. As the structure gets complicated, then this kind of calculation become very, very troublesome. So then we get into the moment area methods, and which will be followed by the so-called conjugate beam approach. And the next chapter will be heavily discussing on the energy-based approach. So the theoretical level of difficulty increases as we go on. But as it turns out, the computational effort or calculations effort that you involve is getting less and less. So it's easier to calculate, but it's harder in the theory sense. Okay, so let's skip the direct integrations. We don't have to hit on that because it's quite limited. So let's look at the moment area methods. So moment area methods, basically it's extended from the moment curvature relationships and directly jumps to the integrations of moment area. So basically, it's that formula there, and you integrate on both sides. Then you know that you're going to get some sort of angle differences between the 2 points, which is equal to the area. Hey. Hello. So the angle difference between 2 points is simply just equal to the area underneath the m over EI line between the 2 points. So what you need to do to do this kind of calculation is very straightforward. First, you get the moment, bending moment diagrams and divide that by EI. Then you have the so-called m over EI plots, and depends on the 2 points. So you identify the 2 points that you are interested in, and the area underneath that curve, this area will then be equal to the angle differences between the 2 points. So theta b minus theta a. Okay, so by itself, it's hard to use because basically, if you want to find rotation angle at B, you need to know rotation angle at A, right? So looking at the equation, it seems to be a little bit hard to use. But for the case that if you know the rotation angle A, you can always go from A to B through this formula. All right, so this is angle difference. Go from A to B. So we use a theta B slash A. And the rotation angle is defined as positive if it goes counterclockwise. And M over EI is defined as positive, it goes up, negative goes down, following the sign conventions of bending moment diagrams. Okay, so that's the first moment area method. And the second moment area method is a little bit complicated. It's basically not talking about the deflections of a structure. It's talking about some projected length on the deformed shape. So this is what it boils down to. We identify, again, 2 points, point A and point B. So you select one point as your reference. Let's say select point A as my reference and draw a perpendicular line and tangential line from B will be intersecting with these vertical lines at one point there. And this distance there we call TA slash B. This is a sort of projected length between A and B. So this TA slash B can be obtained from calculating the centroid measuring from A of this area times the area itself. All right? So this is what it boils down to, this equations. So you can use some sort of integration or calculus concepts to obtain such a relationship. All right? So again, this TA slash B is indicating the projected length with a reference at A. Line is tangential B intersecting with that vertical line. So this distance is TA slash B. And that will be equal to the centroid distance measuring from A times the area of M over EI between the 2 points. Okay, so same token, if I want to do a reverse projected length, let's say I want to draw a perpendicular line there, and then tangential line A intersecting with that vertical lines, and that will be called TB slash A. It's a reciprocal of that, TB slash A. And TB slash A will be equal to the centroid distance there times the M over EI area. So we do have a reciprocal relationship that we can obtain. So that's called second moment area methods. So this is what I mean here. These two relationships. And you can see that they are not the same. They are just some projected length. They are some projected length, and they are not the actual displacements of a structure. So this method is directly obtained from the moment curvature relationships. And as it turns out, it's not a very straightforward and direct applications. All right? We are not getting these deformations directly. This is deformations. This is deformation. This is rotation angle, and this is rotation angle. But we are getting this kind of projected length instead of those deformations that we are looking for. So it's not a very direct approach. So as it turns out, that this kind of approach is also limited. You can imagine that this is also very limited because it's not direct. So it's indirect, and that brings some complexity into your analysis. Okay, so this is a summary for moment area methods. So this is the first moment area methods, talk about the angle differences. And this is the second moment area methods, which talk about the projecting length between the 2 points and their relationships with m over EI plots. Okay, so some example for you. So you are asked, this is a cantilever beam fixed at A and apply a point load at C. So you're asked to determine the slope at point B and C. Point B and C. What is the rotation angle there? The properties are given. So the first thing you need to do is to obtain bending moment diagrams. Bending moment diagrams, M. So that is easy, right? You should know. Getting the M and then divided by EI. Then you have M over EI plot. So this is M over EI. So you see this is M over EI line. So angle. I'm looking for slope or angles. So let's say I want to look for angle B, rotation angle at B. So this is rotation angle at B. And it turns out that point A is climbed. So rotation angle at A is equal to 0. So as a result, rotation angle B is equal to the relative rotation angle change between A and B, because rotation angle A is equal to 0. So as a result, you can directly just use the first moment area equations to obtain the rotation angle at B. So very straightforward. Same thing for C, because A is equal to 0. Rotation angle A is equal to 0, so theta C is the relative angle change between A and C. So there. So calculation then becomes very straightforward. All you need to do is just to calculate the area underneath the M over EI between 2 points. So if you want to calculate rotation angle at B, then you just calculate the area underneath between A and B. Okay, so it boils down to calculation of rectangular area and triangle area. So this is rectangular area, this is triangle area. And it's negative. M over EI is negative, so the area is negative. So rotation angle is negative that number. Okay, it's not too difficult. Right? So same thing, if you want to find rotation angle at C, then you just calculate the whole area between A and C. So you just add on this small area there, and that is it. You can find the rotation angle at C. Okay, is there any questions? We have so many ways to calculate deformations. The best one is the one that is very, very robust and does not give you a lot of room for errors. So you don't need a lot of interpolations. You don't need a lot of guessing. Right? That would be the best technique, right? So you can see that the moment area methods is not a very direct approach. It requires some sort of understanding interpolations. So next is this conjugate beams approach, which is more robust now as compared to the moment area approach. So this technique is based on some sort of mathematical formula that we can identify, basically following two sets of relationships. We call it mathematical analogies. So there are two sets of formula. We accidentally identify that they are mathematically equivalent. So the first set of formula is moment curvature relationship. So this is a moment curvature relationship. if you expand a little bit on that moment curvature relationship, you come out with these two formulas. So this is a d theta dx equal to m over ei, and this is dy dx equal to theta. Right. So these two combined leads to the moment curvature relationship. So that's the first set of equations that we can establish from slope deflections, moment curvature. The second set of relationship that we actually identify is related to external force and internal forces. So we identify that external force, this is external force, is equal to dV dx. V is a shear force. And V is equal to dm dx. Now, when we analyze the structure equilibriumly, try to establish shear force bending moment diagrams relationship with the external force, we have such a relationship comes out, and we just didn't address, put it out explicitly. So we do have such a relationship built in when you try to find shear force diagram, bending moment diagram. We say that slope of the shear force is equal to the distributive force. Slope of the bending moment is equal to the shear force. So we do. Please. You will only need 5 minutes to be lost completely. Only 5 minutes. So just focus. Otherwise, it will take you a long time to try to figure out what this method is about. So this kind of relationship is already built in the shear force bending moment diagrams. And we just explicitly list it out and make comparisons with this moment curvature relationship. So you can see that mathematically this is equivalent to that. And this is equivalent to that. And bending moment here is equivalent to what? So they do have some sort of resemblance that you can identify mathematically. Equations look exactly the same. All right, so this is what happens. This is what we try to solve. We try to solve rotation angle displacement from moment. Right? We have been doing that. Using moment area, direct integrations, we are doing that. So we are not very comfortable about that because the integrations, the moment area is not direct. It's very, very complicated calculation. So, but on the other hand, if we can correlate this kind of mathematical resemblance, we identify that this W is equivalent to that, this is equivalent to that, and this. So they are equivalent in the sense that mathematical equations are exactly identical. So if I ask you to calculate shear force based on some sort of given loading, you know what to do. If I ask you to calculate moment based on some sort of given loading, you know what to do. So this sort of calculations you are more familiar with because basically just equilibrium calculations, right? So this is just equilibrium calculation. But on the other hand, this is very complex integrations or moment area relationship. So if we can just convert these parameters to these parameters, then just we can operate the equilibrium calculations in this domain. That will be easier. So that's the concept of conjugate beams approach. What we try to do is we try to convert all these parameters to this domain and then perform calculations there and then bring it back to the actual beam. So this is so-called actual beam, and we want to calculate the formations of the actual beams. Instead of doing that directly, we convert everything to another domain, so-called conjugate beams domain, and then do some sort of equilibrium calculation in that domain, and then push them back to the real beams domain. So that's what we try to do in this method. So we need to do that. We need to convert everything to the conjugate beams domain, do the equilibrium calculations, and then bring them back to the real beams domain. Okay? So conceptually, it goes like that. And how do we implement this concept? So let's say I have an actual beam. This is an actual beam. I want to calculate deflections. I want to calculate the rotation angle somewhere in the beam. Okay? So I can do direct integration. I can do moment area. So I can do it on this actual beam. No problem. But instead of doing that, can I convert everything to this domain? So by convert, I mean that I need to find m over EI and then consider m over EI as loading. I need to find rotation angle and consider rotation angle as shear force. And I need to find deformations and consider deformation as bending moment. Okay, so that's what I need to do. So I need to find m over EI, and I'm going to convert that m over EI to loading, and then do some sort of equilibrium calculations. So I need to formulate the so-called conjugate beams, which is imaginary, mathematically imagined beam. It's not a real beam. So following these conversions, I need to convert all three of them to that domain. So the conjugate beams, as a result, does not have the same setup as the actual beam because I need to do these conversions. So for instance, on the actual beam, rotation angle equal to 0, displacement equal to 0 at the clamp end. So this is actual beam. So I need to convert these two conditions, boundary conditions, to the conjugate beams. So theta equal to 0 implies V equal to 0 in the conjugate beams. Y equal to 0 implies M equal to 0 in the conjugate beams. So here. So if V equal to 0, M equal to 0, is it still a clamp boundary condition? Of course not. The clamp boundary conditions, you always have a reaction force, shear force, bending moment. So if you designate and say that, oh, shear force, bending moment are equal to 0 at that boundary condition there, then the boundary condition actually is not clamp. It's actually a free boundary condition. Also, look at this side. I know this point, rotation angle not equal to 0, displacement not equal to 0. So converting to the conjugate beams, shear force not equal to 0, bending moment not equal to 0. So here. So they comes out in pair through the correspondence. So as a result, the conjugate beams is not the same as the actual beam because of such a conversion. So as a matter of fact, they are just reciprocal. So originally, you have a clamp end there because you transform into the conjugate beams domain, become a free end. And originally, you have a free end. Now converting there, become a clamp end. So that's the trick for the conjugate beam. So it just converted following these three sets of relationships. And automatically, you can formulate some sort of imaginary conjugate beams, which you can operate on. So this just explains this conversions of the lower two conditions. Now the first condition is simply just means that you take M over EI, converting to loading in the conjugate beams domain. So here. So this is the conjugate beams, and I take the M over EI from the real beams and apply onto the conjugate beams. With that, then I follow. I can calculate the shear force. I can calculate the bending moment based on this conjugate beams loading conditions. So I can find shear force, bending moment everywhere in the beams. And the shear force that you calculated in the conjugate beams is equal to the rotation angle in the real beam. And the bending moment in the conjugate beams is equal to the displacement. So you do the operations in the conjugate beams domain, finding shear force, bending moment, and then you push them back to the real beams domain, and that's it. So these calculations become equilibriums. It's not integrations, right? It's not calculating area. It's simply just the equilibrium calculations. Okay, so imagine that you can calculate shear force. You can calculate bending moment. Then the shear force and the bending moment can be pushed back to the real beam domain in terms of rotation angle and deformation, respectively. So that is it. So instead of doing this doing the deformation calculation in this domain, you push them into this conjugate beams domain, apply the loading, and then follow through by equilibrium calculations. After that, you just push them back to the real beams domain, and you can get the deformations anywhere you want. So this kind of procedure is kind of robust, right? There's not a lot of room for you to make errors, unless you don't know how to calculate equilibriums, unless you don't know the concept of conjugate beams. If you do, then your rooms of error is kind of small. It's very direct, right? All right, so look at the relationship between the real beams and the conjugate beams. So you need to know how to convert the real beams to a conjugate beams. So look at the boundary conditions and conditions on the real beams and converting to the conjugate beams. So for instance, if I have a pin support on the real beam, and I want to convert that into conjugate beams. So the relationships are the lower two relationships. Rotation angle to shear force, displacement to bending moment. So pin support, rotation angle is not equal to 0, displacement is equal to 0. So M is equal to 0 on the conjugate beams, shear force is not equal to 0. So the pin goes to pin, no change. No change. Roller, same. Goes to roller, no change. Clamp, you just saw that. Clamp become free. Free become clamp. Internal pin become internal hinge. Just following the relationship, these two relationships. So internal pin become internal hinge. So they are not our students. They just lost something here. Internal roller become internal hinge, and internal hinge become internal roller. So they all just follow straight from the lower two relationships between real beam and conjugate beams. So these are some examples for real and conjugate beams pair. So real beam, simply supported. Conjugate beam, simply supported. Clamp, clamp. But the other side. This with an overhang become that. So this become that. So it's quite interesting. You're creating an imaginary beam so that you can just use equilibriums. So these are just imaginary beams. So for instance, this is a simply supported with a roller, 3 rollers, and become hinge, roller, and then 3 internal hinges. So we say that we don't have to worry about the stability issue for the imaginary conjugate beams because they are not real beams. They are just mathematical interpolations of relationships. So you don't need to worry about the stability issue. They are not real beams. So all you need to do is to do the conversions, apply the loading, and then use equilibriums to finish up your analysis.